Thank you for having me here. It's a real honor to be here to celebrate this International Year of Light. I'm especially grateful to be here. Actually, a lot of this work that I'll talk about was actually done by David Mackay, who actually is a PhD student here at UIUC, and I actually met him the last time I was here to give a talk, and he's really had a big impact on my group. So I guess the topic here is going to be about manipulating microwave photons, and both kind of on the single microwave photon level, like in a quantum way, and also we'll talk about some sort of other interesting things you can do with light more generally. So this work was done at the University of Chicago. My group was led by David Mackay and these two students, as well as my new postdoc, Watson. The work at the end is actually in collaboration with Jonathan Simon, another professor there, and so I'll tell you about that. So what we're saying is, when you think of International Year of Light, you don't immediately think of microwaves, right? Light, if you say, well, what is light? It's what you see, right? And you don't see microwaves. And so I'd like to sort of address that a little bit. So I think we're celebrating Maxwell's equations. I think we can all agree that Maxwell's equations apply to microwaves, and that's kind of a sense in which we can call it light. But why is it that we don't think about it that way on a day-to-day basis? And the reason is this, actually. So an optical photon, as we saw, it has about an electron volt of energy, right? And so that's like enough energy that you can actually do chemistry with it. You can knock an electron off of an atom. And that allows you to see even a single photon. So actually your eye is sensitive to just a few photons. Actually, Paul Quillot is actually trying to do quantum mechanics with undergraduates using just looking at them. So you can actually measure entanglement with your eye, maybe. And actually there are some animals that also can see single photons. So it's actually in a certain sense, at least with chemistry and sort of APDs and things, it's actually fairly easy to measure a single photon, and we've known how to do it for quite a while. Microwave photons, on the other hand, they're 100,000 times. They have 100,000 times less energy. And so they do not have enough energy to do chemistry. So that's why, if you hold a cell phone on your head, or you don't, start doing chemistry or breaking DNA or anything like that. So one question immediately is just like, how do you even detect them? They're so weak. And another thing I'd like you to think about just throughout the talk is like, what does a photon look like? I think if I say like picture a photon in your mind, you have some picture. For me, it's like one of these little packets or something, but everybody thinks about it differently. And I'd like you to think about what do you think of as a photon, and what does that mean in the context of these microwaves? So, the other thing is, when you see light, you never, in some sense, see the light. You see what was light, right? The first thing you do when light comes in is you absorb it in your eye, and then it's gone. So you see what was, but you never see what is. And I'd like to show how, at least in principle, you can. Well, actually, we'll actually do it. How you can actually measure light without destroying it. And in principle, you could do this with optical photons too, although it's a little harder. Okay, so I will first take you through kind of what I call quantizing the circuit. So basically, how can we take our electrical engineers here, our favorite circuit, or my favorite circuit is the LC circuit, and how can we take that circuit and quantize it, and how can we manipulate and those quanta are photons, and how can we manipulate them? So we'll talk about that, and then I'll talk about some newer work where we're trying to actually make lattices of photons, which we can use to make quantum RAMs, for example. Or we can also start to think about trying to imbue these photons with properties that we think of more akin to particles, like electrons, say. Like, wouldn't it be neat if we could make a photon behave like an electron? So we could do all these crazy things, as Andrew showed with photons, and we could really have this amazing control over them. And wouldn't it be great if we could sort of make them behave like electrons or other particles, and then use them as sort of a simulation? And so, and along those lines, I'll tell you about, this isn't quantum anymore, it's a room temperature FR4 PC board, as you can see. But what we can do is we can actually talk about another topic, which is topology. We can actually make photons see an effective magnetic field. So I'll tell you a little bit about that. Okay, so let's start at the very, very beginning. So what is the absolute most simple thing you can do with light? So the simplest thing is actually a single photon, so one single quanta of light and one single piece of matter, and so for a physicist, I can't solve very much in terms of quantum mechanics. I only know a couple things, so I basically just know the harmonic oscillator, which is just, and you don't really need to look too deeply about this Hamiltonian, but the idea is that we think of a photon as a harmonic oscillator, okay? And so, for electrical engineers, that's going to be an LC circuit, and you'll see that in a minute. And then you think of matter as just two levels, two discrete levels. So that could be an atom and two, atomic levels, or it could be, as I'll show you, a circuit with two addressable levels. But any two quantum levels, and in quantum computing, people have used just about everything. And the idea is that we want to couple them together. That's what this thing means. And all it means really is that we can, let's say we put an excited state atom and it can emit its photon. And this is a cavity. So this is like a box for photons or a hall of mirrors. And so just like one of Andrew's laser cavities. And so the photon can then bounce around for a while. But that atom is still there and it can reabsorb it. And so what will happen is if the photon doesn't leak out, it will just emit it and then reabsorb it and emit it and reabsorb it. And if you could get this rate to happen much faster than any of the decay, the rate at which stuff leaks out of the mirrors, or the rate at which the photons get emitted into some other mode, or the rate at which the atom falls out of the cavity, that has a special name. It's called the strong coupling limit. And basically, if you could do this, if you could get this sort of coupling strength to be bigger than any of the decay rates, you could do anything you want in quantum optics. That's the elemental piece of it. Okay, so that's sort of the goal. And so what we'd like to do is, so people first did this, and it was actually the subject of a recent Nobel Prize with atoms. But what we'd like to do is do this with circuits. So we're going to make sort of an electrical engineer's analogy to this sort of atomic physics experiment. And so the idea here is that our resonator it's very similar. It's a transmission line. So this is a coplanar waveguide, which is basically a 2D BNC cable, just 2D coaxial cable. So here's the center pin, and the ground planes are over here. And then what we do is, if anyone is hooked up a TV, if you plug it in part of the way, you get those lines, which are basically reflections. So these look like mirrors. So if you're not completely connected, you have mirrors, and you can tune that by making that a capacitor and adjusting the capacitance. But basically, this is like a partially reflective mirror, and this is a partially reflective mirror, and so you can get a standing wave here. So it's just like an optical Fabry-Perot cavity. But we can set the wavelength, and we typically set it to about a centimeter or so, and that's in the gigahertz range, so 10 gigahertz or so. And then what we do is we put another circuit, which I'll explain in a minute, and that's going to be our qubit, and that's like our atom. So that's going to use this thing called the Josephson junction, which I'll explain just momentarily. Okay, so these are the elements. Okay, and everything we do is just we put microwaves in at one end, and we see what comes out the other end. And sometimes we'll put pulses in, and sometimes we'll just put DC signals in. Before getting going on some of that, I wanted to just show you what it looks like in the lab. So in fact, it looks a lot like any kind of microwave test lab. There's a lot of Keysight equipment, although at this time Keysight didn't exist. It was still Agilent. And then there's this cryostat here. There's also of course a lot of coffee. So we have. This is called the dilution refrigerator, and it gets down to so here it's room temperature, here it's about 40 Kelvin, here it's about 4 Kelvin, here it's about 1 Kelvin, and then 100 millikelvin, and then 10 millikelvin. So that's 100th of a degree above absolute zero. And you say, why do we get that cold? Well, for a very simple reason is that we want to be able to turn the lights off. So when you turn the light switch off, it gets dark. We take that for granted. But that's again because it's actually a quantum mechanical effect that happens. It's the fact that h bar omega is bigger than kT. That the frequency of light is so high. But if you turn off the lights, your radio still has static, right? So you still have, and in fact, if you just even look out into space, what you'll see is 80 gigahertz, 3 Kelvin cosmic microwave background. So even space is about 3 Kelvin. So that's like about here. And we need to get colder than space. We need to be here so that we can, when we turn off the lights, then there's actually no microwave photons. Because if you want to look at one, there better not be any thermal photons around. So we worked pretty hard to do that, and here's sort of a sample. So let's zoom into there and look at what the ingredients are. So, you know, there's a lot of microwave engineering that goes in. Even just the box is kind of complicated. But you know, in the end, we have this little circuit, and the circuit is fairly simple. So there's this sort of squiggly stuff here. That's that transmission line. We curl it up just to make it fit. And again, you know, it's an LC circuit. That's how you guys should think about it. But what I'd like to point out is that an LC circuit is really, it's a quantum mechanical thing. And it's a harmonic oscillator. And harmonic oscillators have evenly spaced energy levels. And we can think of populating these energy levels as adding photons. So if I put 1 photon in, or 2 photons, or 3 photons, I can do that, okay? So that's great. But of course, the other defining feature of a harmonic oscillator or LC circuit is that it's linear, right? So you can't do a lot of the fun things that Andrew did with just an LC circuit. And in fact, if you tried to just put in 1 photon by shining microwaves in at this frequency, what will end up happening is as soon as you start to get 1, you'll start to get 2, and then 3. And what you'll get is a coherent state. Okay, and that's an interesting state, but it's not a single photon. And with just this circuit, there's no way to do it. So we need something else. Okay, we need what's called a Josephson junction. And so the idea is if you want to do quantum computing or if you want to do quantum optics, what you need is a nonlinear element. So it could be like one of these periodically poled crystals. But in our case, we have, or it could be a transistor if you're doing electrical stuff. And a transistor is like a nonlinear resistor. Okay, and what we have in superconducting circuitry is what's called a Josephson junction. So it's well, you can see it right here. It's basically just 2 pieces of aluminum that are put on top of each other, and there's a very thin, about a nanometer of oxide in between. So the Cooper pairs have to tunnel from one side to the other. And for, again, you know, from an electrical engineering perspective, it looks like a very nonlinear inductor, okay? But it is so nonlinear that even a single photon, so what does that mean if it's nonlinear? So basically if I have current going through it, it will change its inductance a little bit, okay? And in fact, it gets a little bit bigger if I put current in. And if you think about that, what does that mean? That means that if I have current going in, the inductance is bigger, and that means the frequency is smaller. So as I put more power in, the frequency goes down a little bit. And, but if I kind of put it in this quantum context, if I put a single photon in, then the next photon is going to have to go in at a different frequency, okay? And that's the key thing that lets us address just these 2 levels instead of accidentally hitting all these other ones, okay? And so that's why I can call this thing a qubit. They're both almost harmonic oscillators. You know, this is an LC circuit, this is like a JC circuit, but because this inductor is so nonlinear that even a single photon will change the frequency a significant amount, I can think of this as a photon, and I can really put just a single photon in there. And that's going to be kind of the key feature I use to do all the cool quantum optics stuff. Okay? And here's what it looks like. So it's just a, you know, just a C, and then the L is just this tiny little 100 by 100 nanometer overlap there. Okay? Okay. So again, what does this look like in the lab? So what we measure is we do spectroscopy. So we just look at frequency versus transmission. So we put microwaves in, we see what comes out. And what we see is a peak here, okay? But what I'd like you to think about, whenever you see a peak, what that's doing is it's measuring a transition between 2 discrete energy levels. And so what this is really doing is it's telling me how much energy do I have to put in. I have to put in HF, where F is this, to put 1 photon in, okay? So that's what I'm measuring here. Okay, so now what happens when I put a qubit in? So I'm just gonna, I'll just take the first 2 levels, right? So I you know, if I excite the qubit, I have to, you know, I have the same spectrum, but I'll shift it up. Okay, so if they weren't talking to each other, I just would see the spectrum here is 2 copies is right on top of each other. I wouldn't be able to notice. Okay, but now if they interact, right? These 2 levels might, if I put them close to each other, they will split. So whenever you take 2 quantum mechanical levels, or even just 2 harmonic oscillators, actually, they will split. And the splitting is exactly this coupling G, okay, that I was talking about before, the rate at which they exchange energy. And now those widths that I was talking about show up in the width of the peak, okay, that's how long it lasts. And so if I see 2 separate peaks, it immediately means I'm in this strong coupling regime that I was talking about, because, right, the width is, you know, in frequency is how fast it decays. So that's this. And if that's less than the splitting, right, so if there's 2 peaks, it's less than the splitting. That's what that means. So then I can do it. And so in this case, I mean, this may mean something to some people, but the important point is just that, so if I have like, if G is 10 megahertz here, and this is 200 kilohertz, I can do sort of, you know, I can do like, 50 things or whatever before it dies. I could do 50 coherent things. Okay. Now that was a long time ago. That was like when we first got this to work. Since then we've done much better. This is actually still not that recent, but you see it got a lot better. So now instead of so that just on the same scale, right? So line widths are the same, but the splitting is much bigger, and we can and we can do the same thing now. Like the distance is about the same, but these line widths can get even smaller now. Okay, so this is now a slice in frequency. Now what we can also do is we can actually tune these Josephson circuits. We can apply a magnetic field, a small magnetic field, and that frequency moves. And so what we can actually do is we could go from far away, where there's a small interaction, to where they're resonant and they split like that. So the slice I showed you here is just the slice here. Okay? And so the idea is whenever you see a qubit interacting with a resonator, what you should see is some kind of an avoided crossing like this. That's kind of the sign. Okay? So, and the other thing I'd like to note is that you see, okay, it splits here, but even far away, it doesn't really go all the way back. It kind of asymptotically goes back, but we're going to use this shift as a way of actually measuring things. So, okay, so this is again some math, but basically what it says is if I'm far away, I don't get it looks like a piece of glass. So like if I take a resonator and I put a piece of glass in it, it will shift down because the speed of light changes a little bit. Okay, but now I want you to imagine a really weird thing. Okay, so the reason that happens is the glass has a bunch of little dipoles in it, and they stretch and they like it when there's an electric field, and so they slow the light down a little bit. But now imagine instead the glass was in the excited state. So in this case, all the dipoles point with the field in the glass, right? But if the dipoles were pointing against the field, right, then they would always point opposite. And so it would actually cost extra energy. And so instead of shifting down, it would actually shift up. Okay? And so basically, if we look at how this peak shifts, so if there was no qubit, the peak would just be here. But if the qubit's in its ground state, it will shift down, and if it's in its excited state, it will shift up. Okay, and so we can actually detect the state of the qubit. Okay, and then what we do is we drive this qubit, so we force it to oscillate between 0 and 1, and then we can just look at, we just let's say measure on this peak, say, and or I guess on this peak, and then we'll see that it goes up and down. So we can make it sort of oscillate, and the fact that this starts here and then goes to here is kind of indicative that it's really a bit. It has just two states. This is what happens if you have a two-state quantum system. Okay, so we have our qubit. We know we have a way of measuring it, and we can do it. And so I'd like you to keep this in mind, because this is going to be useful for also how we measure the photons. So we're going to sort of reverse this. So the idea, anyway, is that this still. So just to give you a vague idea of the math here, this is a harmonic oscillator still. Like whenever you see A dagger A, that means harmonic oscillator, and whenever you see sigma Z, that means spin. But what you see is that the frequency of this harmonic oscillator now depends on the state of the spin. So that's kind of what this picture means. Okay, so that's what's happening there. Okay, but now that was just a way of writing this equation. I could have, right? I mean, there's no reason I had to group it this way. I could just as easily have grouped it this way, right? Where I put the A dagger A with the sigma Z and separate it out. So now it looks like a harmonic oscillator, where the spin frequency is shifted by how many photons are in there. So I could use the resonator to measure the spin, but it's not like one of these is right and the other is wrong. There's just two different ways of writing it. In fact, both things happen. And so if I look at the qubit now, right, and I look at and I now turn up the power of the measurement. So here's about 1 photon of power, and here's just about 20. So these are very small powers. So just to give you an idea for fun, this signal is probably about minus 140 dBm, and so this one is then minus 130. So really, really small powers that are happening here. And you see it shifts, so here's where this line is, and it shifts to here, and it also gets fat. And it gets fat actually, because the reason it gets fat is actually interesting, so that seems like it's a bad thing, but that's actually quantum mechanics. So the fact is that these photons, right, the electromagnetic field, it's not continuous, it's actually quantized, right, it's photons. And this number of photons is not that big. And so this is the average number of photons, but whenever I have discrete things and I give you an average, really you should imagine that there's going to be square root of n fluctuations. That's called shot noise, right? and you will, and that's what this is actually, so the width of this is actually square root of n. And what it is it's a lot of peaks that look like this, all just sort of shifted by, on average, 20 photons, but varying by square root of that. Okay, but now what happens if, yeah, so this is kind of just a depiction of that, right? So you've got lots of different peaks, you add them up, you get that, okay. But let me ask you a question. What happens if, the shift per photon, so, this number, but that shift per photon, what if that were actually bigger than this line width? So here, it's smaller than the line width, they all kind of blur together, right? But what would happen if it were bigger than that line width? Well, then you would see this kind of data. So we did spectroscopy with a stronger coupling and a narrower line width. And what you see is that instead of just getting a big, broad peak, you actually get is a Poisson distribution of different peaks, which this one corresponding to nothing, this one corresponding to 1. So each different number of photons actually has a different shift, and you can measure that. And so, this was back to that question about like how do you picture light, right? So if you have a coherent state, right, that's actually just a sine wave, right? So, and it could be a laser going at 500 terahertz, or it could be something you hear with your ears, or it could be some microwave, but it's just a sine wave basically, and this is what it looks like in terms of its photon number distribution. And if it were a higher number, it would look more Gaussian, but it would still have these individual peaks, and it would still have a width which is roughly square root of n. And then if you have noise like static on your radio or sunlight or whatever, then it actually has a very different distribution. So it has it's still the same mean number, so they're both mean of 2, but they look very different. So we can actually, and when we do this, the photons are still in the cavity. We're not actually killing them. The qubit just feels them. It's sort of like it's being pushed on by the photons. It's almost like a radiation pressure kind of thing. So we can measure these photons. Now the question is, could we create them? What would be really nice is if we could make single photons. It's like one of these like nice things about these like parametric down conversion sources is that you can make single photons out of them. And what would really be great is if we could just do that with sort of like a gun. We say, I want a photon now, and you just get a photon. Right? And we have this qubit, and this qubit is sort of right, there's only one there, so you can't put more than one qubit excitations, because there's only one physical qubit, and it can only store one photon. So how do we do this? What we do is we put a pulse on it, so we just hit the qubit for a very specific amount of time so that it goes to its excited state. And then we just wait, and it will decay, that photon will decay through the resonator. And so what we do is, you see, we just put a pulse on the qubit, and what we see is that oscillation again, okay? But now, so it doesn't matter how high up we go in terms of power, we still get the same sort of maximum amplitude in terms of the fluorescence, in terms of what comes out. And so if we just kind of go right to that point, if we just set our pulse there, then we can get out exactly a single photon. Actually, what's even more interesting is if you go here, you can actually get a superposition. You could get 0 plus 1 photons, or 0 minus 1 photons, or whatever phase you want. So you can really have a lot of control. And more recently, we didn't do this in this experiment, this was a while ago, but more recently people have been tailoring how they couple out, so you can actually tune the phase and amplitude versus time, so you can really completely engineer the waveform of this single photon. So that, really to the last topic. The other thing we can do is we can measure it. So we can use that same technique from before, and we can now measure the tomography. So we can take this single photon, for example, we can measure everything about it, basically. So we can measure all of its properties. This is like kind of its amplitude. This is, and these are the two quadratures. This is sort of the in-phase, the cosine part and the sine part. And we can measure that as a function of what we do to this qubit. And we can make a map. You can also, you can also make, so you can make really exotic states. You can make a state, so this was done in another lab where you'd say make a 0 plus 5 photon state. So there could be 0 photons, there could be 5 photons, but there can't be 1, 2, 3, or 4, okay? And if you do that same tomography, you get this really interesting looking structure here that's got like 5 lobes and some interesting structure in the middle there. So, yeah, and you can make Noon states, which are states which, there's 2 different resonators, and you either have you have N photons, but they're either all over here or all over there, but not, not some even mixture. So you can do things like that. People have now made 100 photon Schrodinger cat states, so you can make really crazy kinds of quantum optical states. And some of them are even useful. So, okay, so this is sort of quantum optics. We can manipulate single photons. We can do what we want there. Now let me just tell you a little bit about kind of where we'd like to move from there. What do we want to do with them? So, so here it's a similar kind of a circuit. It's got a little bit more stuff. And I just want you to look here where basically instead of just one resonator, there's now 3. And these are just really LC resonators, like actually. But there's these 3 resonators. And so when we do that same thing where we scan the magnetic field, now you see 3 avoided crossings. So 1, 2, 3, okay? And so we can, so one thing we can do here is, so we could actually, if we go do this quickly, we could actually convert the qubit to a photon. But the problem is, it's very hard. The question is, how can we get our photon from the qubit? We could get it into this lowest mode, but how do we get it to this resonator or this resonator? It's kind of, because we have to sort of go through the first one to get to the second two. It's sort of, it's like this one is kind of hidden in some sense. So, and so actually we're gonna play a trick which is basically what we're gonna do is we're gonna make a quantum FM radio, okay? So what you do with an FM radio, right, is you frequency modulate. So you take your carrier tone and you frequency modulate it, right? And then what happens is you get sidebands, okay? So think of this as this is our qubit, but think of it like a radio carrier, okay? It's a 1 photon radio carrier. It's a pretty weak radio, but you can still think of it like kind of like a radio. And then we're gonna move it up and down. And what we'll get is we'll get sidebands. So there'll be a first order sideband. Actually, there'll be like a whole series of them with Bessel functions and whatnot, but the first one will be the biggest. And if we make this, and the cool thing is, we can make these sidebands appear basically anywhere we want. And so what we can do is just make them appear at exactly the mode we want, okay? And so we're gonna do a really neat thing, which is that we're going to basically, you know that process I was telling you about where we have the photon exchange back and forth. So we're going to do that, but not only are we going to do that, but we're actually going to do it for multiple modes. So this is kind of what the data looks like. So what we do is if we modulate it at the frequency such that this lines up with the bottom one, we'll get these oscillations. And if we do it with the middle one, we'll get these oscillations. And if we do it with the top one, we'll get these. And what you see is, so you see these oscillations now are literally that photon going back and forth between our qubit and this resonator. So between one of those LC resonators and one of and the qubit. And you can really tell that there, usually when you drive something like this, it will kind of go to the middle. Because you're sort of driving it, and sometimes you lose, sometimes you gain. Eventually, it kind of decays to the middle to some 50% kind of thing. But which is kind of related to why some of those plots that you saw earlier had sort of this 2-to-1 contrast. But here these actually go to 0, and it's because there's actually only a single photon, and it's just a single photon that just goes around and around until it eventually dies. So this is really neat, and what it means also is that we can put as many modes as we want, and we can store single photons in each one. So we could, for example, if we want, we could store a photon in here, then do something else to the qubit, and then store that state over here, and then do something else to the qubit and store it in there. So it's kind of like a memory, okay? And so we have one qubit, but now we have, and these qubits are fairly complicated. We use that whole rack of test equipment to measure them. And what would be cool is if we could have, sort of a memory for those qubits that we don't, with just one qubit, we could actually store lots of bits. And so the idea is these are harmonic oscillators. We can't use them as qubits by themselves, but we can store things in them. So we can sort of store any state we want, by just sort of doing the appropriate phase and time in this oscillation here. So that's kind of the idea, is that we can do that. And what we've done now is we've made a bigger circuit. So we've got, it's one qubit over here, and there's a readout mode, which is not so important. But now we just have n of these resonators. So there's 22 of them, actually. So we can actually make a large scale, well, large scale for us, but 20 bits of memory. And so the cool thing is we only need 1 bit and 1 bit of control stuff. And the resonators have some nice properties with respect to bits. So this is what it looks like now. We're still it's not quite as clean as before, but there's actually 20 modes here, and you can still see all these oscillations and stuff like that. And we can actually we can also entangle let's say this mode and this mode. We can do kind of whatever we want there. So I think this is a very exciting direction for quantum computing. But the other thing I'd like you to think about is that this looks a lot like a lattice, right? Like a photon can kind of go here, then hop to here, then hop to here, then hop to here. So it's kind of like a 1D kind of chain, like a like a polymer or something like this. And so you can start to think about these photons as like particles that are hopping in a crystal lattice. And so I'd like to kind of explore, in the last couple of minutes, I'd like to explore that kind of analogy here. So it's a little blurry, I guess. But the idea is you can see this is sort of a lattice. There's a grid. This is actually a 2D lattice. And the idea is like we'd like to think of this photon as sort of hopping around this lattice, and we'll see that. And but what we'd like to do is make this photon think that there's a magnetic field. So photons don't see magnetic fields, right? I mean, it's linear, so they just go through each other. Like if I put a photon, it doesn't curve in a magnetic field like an electron does. So if I put an electron in a magnetic field, I apply like the magnetic field out of the page or something, it'll circulate around, right? It's called a cyclotron orbit. And so if I take like a 2D semiconductor, say like gallium arsenide or something like this, and I apply a big magnetic field, I will, in the middle, it will actually localize. So everything is just in these closed orbits, and it's an insulator in the middle. But on the edge, actually, a funny thing happens. So the electron, right, it comes, it sees the magnetic field, tries to do a cyclotron orbit, but then it hits the wall, okay? And then it bounces, right? But then now instead of going back, right, actually the magnetic field curves it back this way again. So it actually just keeps going along the edge. And so you may have heard of the fractional quantum Hall effect or the quantum Hall effect. This is how resistance is defined, actually. And that's sort of how this works. So all the current there actually travels along the edge, okay? And an interesting thing happens. One of the reasons it's such a great standard is that it's very insensitive to disorder, because look what happens. So I have this thing. Now imagine I have like, the edge is a little rough, so there's a little thing here, right? So it goes here. Now normally it would just bounce back and then you'd be in trouble, right? But what happens with the magnetic field is it actually just goes, it has to go this way. It has to always go in this direction because of the magnetic field. And so it will actually just go right around it. So it actually just routes right around it, and you get no backscatter. And so that's why, even though these samples are often not perfect, and in fact they actually work better for the standards if they're a little bit imperfect, they still work basically perfectly. So the question is, could we get a photon to do this, right? So this works all because of the Lorentz force, right? Like an electron feels a force which is QV cross B, but of course photons have no charge, right? I mean, we all know that. So how can we do that, okay? And and it's maybe an interesting question if you could even do this for an electron. And it turns out you can, and the trick is you need what's called a spin-orbit coupling. So what is a spin-orbit coupling? Well, I'll explain it in the context of this photons in a moment, but what it really is just that the spin up and the spin down should sort of see different, like they should hop differently. They should travel differently in space, okay? And if you can get it to do that, at least in principle, you can make it, right? And you can see, like, basically the magnetic field is something that affects spin up differently from spin down. So, it's at least one of the properties. And so if you could get something that happens like that in a spatial extent, you could imagine that you might be able to create something that looks like a magnetic field. And actually, this happens naturally in things with heavy elements because the nucleus makes an effective magnetic field. And this class of materials that are called topological insulators. And it's gotten a lot of press lately, and it's kind of an interesting subject. And the question is, could we do this for light? Could we make light a topological insulator of light, or a topological circuit? So there have actually been a lot of thoughts as to how to do this for different things. So this is actually these sort of waveguide structures similar to what you were hearing about at the end of the last talk. This is kind of a microwavy sort of thing with magnetic things, and this is sort of in fibers, well, sort of dielectric waveguides for optical photons. But let me tell you about our approach. So let's just start at the simplest thing, no topology, right? So we just have LC, 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 that forms a transmission line, and that looks like light, right? Because we have a dispersion relation, which is linear, and so microwaves just can travel along there. So that's how we use our cable TVs and all that kind of stuff, right? And the idea is that if we could somehow, what we'd like to do is make it so what we're going to do is essentially make a second copy of that and call the different ones the spin, and then we're going to braid them such that they they actually behave differently depending on which one they're on. So let me kind of take that a little bit more. So, okay, so we have 1D thing, so L's and C's, okay? So then we want to go to 2D because we want to see the circulating effect, so we need 2D. So we just take this and make a 2D grid of it, so it's fine. And that looks like here, so instead of just, now there's 2 dimensions, but again, it's just kind of like light, to at least at low momenta. Then, okay, so now we need to do the spin. So how can we have a spin? And we could use like something like polarization, but in microwaves, typically we don't usually use the polarization. So what we're just going to do, we're going to do the simplest thing is, spin it doesn't have to be spin. It could just be anything, any 2-state system, right? Like our qubit wasn't a spin really. It just had 2 different states. So what we're doing is just going to make a separate copy. So we literally just take every element in the first one and we just make a copy of it, okay? And we can call this one A and this one B or something like that. Okay, so now we have 2 degrees of freedom. So we at least have the right number of degrees of freedom here. Okay, so there's some math here, but the idea now is like, so there's site A and site B, and what we want, so what a magnetic field means, one way of thinking about what a charge in a magnetic field is that when I go around a circle, I pick up a phase, okay? I pick up an Harmon-Bohm phase for quantum mechanics, but basically, I don't come back to exactly where I started. Even though I move around, because there's a magnetic field inside, I feel something different. And so what we'd like to do, and if you want to say that there is let's say a quarter of a flux quantum, what that really means is that you have to go around twice, say, for example, before you come back. So, first spin would have actually 4 times. But anyway, so this is where the braiding comes in. So we're going to have these connections between. So here's our LC over here for A and B, and each site has one of them. So this is one site, and this is the A part and the B part, and we have that for each of them. And we're going to have these special couplers. So the 0 coupler is just they go straight. So A goes to A, B goes to B, and then so let's just follow an A1. So A goes to A, okay, and then this is also a 0, so A goes to A. But now this one is a pi over 2, and what that means in this case is that basically like A goes to minus B, and B goes to B. So what we went around the whole circle, and then we ended up at minus B. So we have to go around again, and then we'll eventually get to A. So basically, when we go through this, we get sort of this phase, which again, the way we do this in practice is really simple. We just change the connection. So inside here, there's just wires, and they either go just straight, or like in this case, they actually go from this one to this one, and this one to this one, and we can also twist them to get a sign. So we can basically couple A to A to B, or A to minus A, or A to minus B. Okay. And so we do this, and now when we go around the loop, what we find is, if you work it out, basically what you find is that if you want to say the mode that sort of when it goes around the loop, it doesn't matter. It's actually a superposition. So it's like a kind of a circular polarization of up plus I down, or so A plus IB and A minus IB are the 2 things that kind of go like this. And now this has sort of a chirality. And so what we're going to find is that one of these modes actually propagates along this way, and the other one propagates along this way. So and what you'll see is it's actually going to recreate a lot of the features that you see in a magnetic field. So again, this is the circuit. And this is like what the band structure looks like. And it's complicated. You don't need to understand all of it. They're just for people who care. So there's these Dirac points, which make kind of like graphene. So you can get physics like that. But the thing I'd like to point out is that there's this gap here. Okay? And in this gap, but in this gap, it's not just totally empty. There's actually just these very few states. Okay? And what these states are going to turn out to be is the edge states. Okay, so if we excite here and we excite in the bulk, we should see kind of localized stuff like those cyclotron orbits. And if we excite at the edge, we should see these states, which are going to turn out to be the edge states. So let's look at the spectrum. So what we do is we just, like with a network analyzer or something, we just drive at one spot and then look at another. So in this case, we're going to drive in the bulk and then look someplace else in the bulk. And what you see is that there's this gap here, right? And that's this gap. Okay. There's also some smaller gaps in other places, but mainly there's a big gap. There's nothing there, so that's a good sign that we've actually created the thing we want. And then if you look at the edge, you see that in that same place where there's a gap in the bulk, there's not a gap. It doesn't look continuous because this is only a finite length, so you actually get discrete peaks, just like you would in like your Bode-Lock laser or something like this. It just takes some time to get around. But basically you have these modes. And so now what we're going to do is, what we can do, but this is actually big, right? So unlike like a real material, we can actually just go in and measure each different site, okay? And so what we do here is we in this scenario, so we probe here, and we put a drive here, and then we just probe everywhere, okay? And what you see is that it's localized, right? There's this sort of this orbit, and it decays exponentially, and so it doesn't ever touch the edge, basically. Okay, so we could have, so this is kind of our cyclotron orbit. And if we look on the edge, we see actually that it gets localized to the edge. So it's only on the edge, and it doesn't. And you can actually see, I think this is where we put the probe, and that kind of puts a little disorder. And so it actually will go around the disorder as well. So it has that property as well. So you can actually make light go around obstacles, which is kind of a neat thing. So we can do that, and then we can also, the other thing that's kind of neat, so this is kind of in space that we're looking at it, so there's no time here, but we can also, these are actually very slow, so these actually are only, it's not even really microwaves, it's actually 100 kilohertz, so it's RF, and it goes very slow, so I mean it's, I forget, it's, well, you can actually see the speed here. And so we can actually just, on an oscilloscope, we can detect it. And by measuring both sides simultaneously, we could actually even, spin resolve it. So we could actually tell the different spin components. And so what we've done here is we've measured, we put an excitation in here, and then we measure at each site versus time around the edge. And and both the A and the B, and then we color the the one spin blue, we color the other spin red. Okay, so one of these rotating states this way or rotating state this way, and what we see is that the blue state actually has goes in one direction. So it's kind of like if you have like a plus sign or a minus sign or something like this, right? Like it would circulate one way versus the other way. So it goes, and so this one is going around, and then it goes all the way around, and it comes back. And this one goes around the other way and comes back. And so this one is driven here. Okay, so that same edge state that we looked for before. It turns out it's not totally obvious, but you can sort of figure it out. But it turns out this gap has this protection property that it actually does this thing. Not every gap has it. So this one up here actually doesn't have that property. And so here what happens is actually just garbage, right? You put it in, and everything just goes everywhere. So it really is a special thing. It's not like this would just happen, without this sort of special structure. So we can see that. And then the other trick that we can do, which we can do with circuits that are really hard to do in, let's say, like a material like graphene or something like this, is that we can actually we can just take wires and hook it up however we want. So we can actually hook it and hook it with a twist. I mean, you sort of see this with nanotubes, right? If you hook it with one orientation, you get one thing, a different orientation the other. Although it's not exactly a twist, it's more like a shift. But anyway, so and then you can make like a Mobius strip topology, right? And then there's essentially only a single edge, right, that just goes around and around. And so now what happens is it goes around and around, but because of the twist, it switches from being spin up to spin down across the boundary because of the way that we twisted it there. So actually it keeps going around in one direction, but it keeps switching to the right spin there. So it's kind of neat. And what we'd like to do with it eventually is to actually do a quantum version in the microwaves with qubits, and then we'll get interactions. And just like this is kind of like a Hall kind of effect, like a classical electromagnetic field right now, because this is all classical. If we can put qubits in and get them to get these different photons to interact, we might hope to see a fractional quantum Hall type physics, which would be really neat. So with that, I'll conclude. So, again, I hope I've sort of convinced you that you should really think about microwaves as quantum objects, and that we can do a lot of things with them, and told you a little bit about how we do that. And then, and I think it's really exciting that we can start to make these photonic materials. One example is this topological type circuits, but there's a lot of other options as well. And so we're just very excited about it. And thank you.